let's start. So today we continue with the WKB story, and I guess first I should recall you the context, which is quite elaborate. So we are looking at the Schrödinger operator with potential. We're keeping the coefficients, and in particular we pay attention to this parameter h, which is supposed to be a small parameter. So we're interested in the behavior when h is small. So we assume many things about the behavior of the potential. Let me redo, or try to redo, the drawing that I did last time. So we assume many things about the potential. First of all, it goes to infinity when x is sent to plus or minus infinity. So as depicted here on the drawing. So we fix a window of energies, something like this, and we assume that in this window the equation v of x equal to E admits two solutions. So for instance here I choose some energy, so that's the energy level, and we obtain a segment where v is smaller than E, and so these are the endpoints of that segment. So we say that when x is smaller than A or x is greater than B, this is the forbidden region. Now x equal to A or B, these are turning points, and finally x between A and B, that's the allowed region. And actually in the allowed region we have the classical mechanics story, and for us this classical mechanics is the following. So this means that there we can have a dynamical system. So x dot, the time derivative of x, equal to 1 over m of p of x, where p of x is equal to the square root of 2m e minus v of x. And we can choose here any square root. So sometimes I assume that the square root is positive, but sometimes I assume that it's either positive or negative, depending on the context. So actually it's convenient to introduce a similar quantity defined in the forbidden region, which we call q of x, and this is the square root of 2m v of x minus e. And I have several more assumptions. Well, let me go to the next blackboard. So there are more assumptions on V. First of all, let me denote it like this. Minus Fa is equal to V prime of A. This is smaller than 0. And Fb equal to V prime of B is greater than 0. So it's actually as on the drawing. And we also assume that V prime over V and V double prime over V are bounded for x large. So somewhere going to infinity in both directions, those two quantities are bounded. Well, lots of assumptions. Now, we're formulating the following theorem based on those assumptions. So let's assume that E is such that the following integral, and I here stress the dependence of A and B on E of P of x dx 1 over h, right? No, not 1 over h, sorry. Is a multiple of P with a coefficient which is half integer. So then there is a point E tilde of the spectrum, of the true spectrum of the operator H, such that the distance between E and E tilde is bounded by some constant. The constant depends only on the window, so the constant is the same in the whole window times h bar squared. So I think that was the context we formulated last time. And I also told you that I don't plan to prove it. However, I'll give you something which is not a proof, but which is some kind of reasoning. And you will see why I don't want to give you a proof eventually. So not a proof of this theorem. So first of all, let me recall the following. So this will be a kind of lengthy, not a proof. Before we already proved the statement which is somewhat similar in nature, but here instead of h squared we had an h, and that had a very simple proof, right? A very short and simple proof. And it was based on the following idea that we were choosing a function of that form, a of x times such an exponential. So then we cleverly chose s of x. We chose a to be more or less arbitrary with some rather loose conditions, and it gave us the spectral estimate. So now we try to refine this picture. So we try to choose a better. As we will see, it leads to a lot of problems. We're going to try to solve those problems. This will lead to more problems, and so on. But eventually it converges. So we'll see how it goes. So that's roughly the idea. Now let me recall a lengthy formula that to get the coefficients right. So let me write a lengthy formula that we derived last time. So that's the formula for h minus e acting on psi of that form. And it is like this: v minus e minus 1 over 2 plus 1 over 2m s prime squared times a minus I over h over 2m 2a prime s prime plus as double prime minus h squared over 2m a double prime, and this is all times exponential of is over h. So that was the formula we derived last time, and so we chose s to make the first bracket equal to 0, right? So that was the idea. So choose s such that s prime squared 1 over 2m plus v minus e vanishes. So this implies s prime equal to the square root, which may be positive or negative, of e minus v. And maybe just as a remark, so right, that's exactly the expression for p of x. So this means that our wave function in the allowed region, so this expression will be equal to something like exponential integral plus or minus I over h integral p of x from some, or maybe p of y dy from some point that we're gonna choose in some way, integral from x0 to x. We can also take, we'll be taking some linear combinations of those exponentials, right? So these are all valid choices. And in the forbidden region, what happens, right? Here we have a negative thing under the square root, so this is actually pure imaginary, and it is plus or minus I times that function q of x that I introduced, right? So this will be an exponential of plus or minus 1 over h and then integral of the exponential q. Right, so that's how it's going to look like. Okay, now we can make further choices. You see, we're thinking in some way that h is a small parameter, so we killed the first term on the right-hand side by this choice of s, but now there is the second term which is proportional to h bar, so we can try to kill that by the choice of a. Right? So let's make this choice. So let's choose a of x such that 2a prime s prime plus as double prime equals to 0. Well, and in principle, in each of the regions, in the allowed region and in the forbidden regions, it is possible to make such a choice. So let me also rewrite it in terms of p So this is 2a prime p plus ap prime equal to 0. Then it's easy to see that this equation is solved in the allowed region by the following choice. A is a constant divided by the square root of p of x, and similarly in the forbidden region it will be a of x equal to a constant divided by the square root of q of x. So this is a kind of better choice because we killed now two terms. Maybe I rewrite for the future use, I will rewrite the result. So the result actually is simply h squared over 2m. Now let me rewrite it as a double prime over a times psi. Right? So I multiplied by a, I divided by a, right? So I got back my psi, and so that's the right-hand side. That's how my Schrödinger equation is not solved by the psi. So now let me try to summarize what kind of function we are trying to. I'm trying to sell you a function which will prove the spectral property for H. So the WKB function. So psi of x. And I'll write here something, but then it will have to be modified. So first of all, let's say for x smaller than a, right? So for x smaller than a, I am in the forbidden region. And in the forbidden region, well, I have two possible exponentials that I can write there. And I guess I will prefer the following exponential. Let's say I will be integrating from x to a. Here I will write q of y dy, and here I can choose the sign. So that's, I think, the exponential which will be falling when I go to minus infinity. So the other one will be relatively rapidly growing when I go to minus infinity. If I want any chance to be an L2 eventually, I need to choose this exponential. And here there will be some constant. Let me call it forbidden minus constant divided by the square root of q of x, right? So then in the allowed region, let me, so this will be constant, some c allowed, divided by the square root of p. And here let me write it in the following way. I'll write it as a sine function, again, integral, sorry, here 1 over h, of course. 1 over h p of y dy plus some unknown phase delta, right? So I take a linear combination of two exponentials. And here I will have c forbidden plus over square root of q of x. And here an exponential, again, if I want to choose it to be the following exponential, this will be that one. X greater than b. So that's our candidate for the spectral estimate. So notice that roughly speaking, we imagine we imagine the following behavior. So that's, let's say, that's our potential. That's the energy level, right? That's the allowed region. Outside is the forbidden region, and we imagine the following behavior of the function psi. It rather rapidly oscillates here in the allowed region, and in the forbidden region where there is no classical mechanics, it goes to zero, also probably rather rapidly. I don't know how rapidly, maybe even more rapidly than I'm drawing. So that's roughly the picture that we imagine, right? So this rapidly oscillating exponential and rapidly falling exponential outside the region where classical mechanics exists. Now, that's all very good, but there is one small problem with this story. You see there are those square roots, right? And p of x and q of x, these are the functions which are equal to 0 at the turning points, right? So in fact, those functions that are right here, they have the following problem. Actually, here the amplitude of those oscillations is growing. And also, this function, which is, yes, it is falling very fast in the forbidden regions, but it wants to go somewhere to infinity near the turning points. And this is no good. So those functions, they typically do remain in L2, but already this result h minus e, the image under h minus e, it will have, you may check, it will have already two series singularities at the turning points. So it's already the result of applying operator h to this stuff. It's not in L2. So it's no good, this function. Okay, so what should we do? We have to, so the first amendment to this WKB ansatz is as follows. Okay, let's introduce more regions. So I will say that this is valid for x smaller than a minus epsilon. So this is valid for x bigger than a plus epsilon. So here b minus epsilon, and here b plus epsilon. So this behavior I prescribe here. Now, what happens near the turning points? I think I chose to consider the turning point B. So near the turning point B, right, let me look at the Taylor series of V. So V is equal to E at the point B plus the derivative V prime of B. So this is what is called FB, the force at the point B times x minus B plus higher order terms, right? So then, okay, let's try to approximate the potential near the turning point by the linear term. So then, what will happen to our Schrödinger equation? So the Schrödinger equation says that so the Schrödinger equation says this. So now we approximate the Schrödinger equation and we replace this guy by the linear approximation, right? So it does not quite imply, but we are looking at the equation now, psi double prime, and what will happen here? We'll have 2f fb over h bar square times x minus b times psi. Well, we kind of know that equation, right? We looked in some detail at solutions of this equation, especially if we make a change of variables, let's say z. Here there is a kind of, here it starts getting a little bit ugly. So you see, I make a change of variable z equal to this coefficient to the power 1/3 times x minus b. So why 1/3? So that's because you see that here there is a second derivative, right? So when I make a substitution, there will be like a power 2/3 coming from here, power 1/3 coming from there. So this will cancel the coefficient. So with respect to z, we obtain the following equation: d to psi over dz square is equal to z psi of z. So that's the Airy equation. So we actually started this equation last time. And now we can try to fill in what happens between the regions, right? So for instance, around the point B, for x smaller than b plus epsilon greater than b minus epsilon, we can try to say psi of x. Well, what do we say? So we can say that this is some new constant, let's say cb, times the Airy function. And this Airy function, well, we have to put in this ugly argument. So we can try to do that. Now, of course, we have all those many coefficients, right? And in particular, we can try to align the asymptotics of this one, right? So that's the Airy function sitting in this region. We can try to align it with the WKB asymptotics on the two sides. So so the next question is to find relations between what? Between the constants CB, C forbidden plus, C allowed, and delta. So this is also known as the connection problem. So aligning the asymptotics of the Airy function with the WKB asymptotics on the left and on the right normally should allow us to relate the constants in those solutions. So let me show you a little bit. So here it becomes really somewhat ugly, but let me show you just a little bit of how it goes. So for instance, let's match the asymptotics of the Airy with the WKB asymptotics on the right. So this means that we do this matching around this point. So what happens? Right. Now, in order to do that, right, I need to know how this thing behaves, right? So so now what do I have? I have q of y is equal to the square root, and here 2m. And here maybe you should watch my hands. How is it? fb times x minus b, right? So this means y minus b. So this means this integral q of y dy. So this will be 2/3 2m fb 1/2 times x minus b to the power 3/2. And this means that the asymptotics of the WKB function, it will be, so roughly, right? So the WKB asymptotics, it will be what? CF plus, now what? Divided by, well, as I promised, that's not very nice. So the square root of the square root, right? X minus b to the power 1/4. So that's this guy. And now exponential of minus 1/h 2/3 2m fb 1/2 x minus b 3/2 times whatever, something else. Right, so that's the asymptotics that you get from the WKB analysis. Now the asymptotics of the Airy function, last time we invested a huge effort into computing the asymptotics of the Airy function. So let me write down, or let me try to write down the answer. So it will be the constant CB divided by 2 square root of pi, right? So remember this 2. And then, well, let me just write down what I computed. Hopefully it's correct. So it will be 2 mfb over h squared to the power 1/12 x minus b to the power 1/4, and then exponential of minus 2/3 2m fb over h squared to the power 1/2 x minus b to the power 3/2. So that I obtained by substituting this ugly argument with a coefficient into the asymptotics of the Airy function that we computed last time. Now, so as you see, fortunately, the top contributions, they match. Now, this behavior matches. And then there is a somewhat ugly but easy linear relation between the coefficients, right? So there is a linear relation if we match the asymptotics. There is a linear relation between the coefficients. So let me write it down. So it says that the coefficient CB of the area is 2 square root of pi coefficient C forbidden plus times whatever 2m FBH to the power minus 1 over 6. So there is this linear relation. Now, in the beginning, I must say, I was planning to torture you with the comparison of asymptotics on the other side. Frankly, I'm not sure it's a good idea. Let me simply tell you what the answer is. So, so here is the comparison at b minus epsilon. It tells you that C allowed is equal to the 1 minus square root of pi to m FB h bar to the power 1 over 6 of the area constant. So now, of course, you can substitute one into the other, and we obtain CA is equal to CF plus. So that's a kind of beautiful relation between the constants of two WKB asymptotics. And you know, this coefficient 2, where it comes from. Remember last time I told you that in the area asymptotics everything is important. So one of the things which was important was the coefficient 2, which was present in one of them and which was absent in the other one. So it's important because that's this coefficient 2. That's the coefficient 2 which tells you how to match the WKB asymptotics if you want to interpolate between them using the area. And then also, right, we have one more parameter to determine what is this delta. And this delta turns out to be equal to pi over 4. Which pi over 4? Remember, there was a pi over 4 in the oscillating area asymptotics last time. So this is hugely important. Let's say in the scales of importance, this is important, but this is much more important. Okay, so there is this delta equals to pi over 4, and that's again by asymptotics matching. All right, so so far so good. Now maybe a remark. So there will be two parts of that remark, a small part here and the big and important part on the other part of the blackboard. So you can do the similar matching at the point A, right? And at the point A, it would also give you a relation between those two constants, right? So the relation between those two constants will be given by, again, the similar relation. So C allowed will be equal to twice, or maybe let me call it C allowed prime, twice CF minus. And I'll now say why I write C allowed prime. So that's because in the allowed region, we can write two different WKB expressions. So actually, let me put here prime. So one of them is the one that I wrote. So sine 1 over h integral from a to x p of y dy. Now we know plus pi over 4. And then, to be honest, when I did a matching at the point B, I wasn't doing a matching with this one. I was doing a matching with the expression like this. Right? Because I want to control to compare with the asymptotics of the area, I need to write this expression. So I need to choose just a different point, x0. Remember, when you define the function s, you choose your point x0. And to do comparison with the area at B, you need this guy. But to do the comparison with the area at A, you need that guy. Right? So actually, we're getting two different WKB expressions. A priori, they have different coefficients here, different coefficients of the allowed region. Now, if you want to eventually use that function somewhere, you need them to match. And that's this matching relation which will eventually give us the relation. Now, okay, so we want those sine functions to be either equal or maybe opposite to each other, right? Because we can also put those coefficients to be one to be minus the other. So the realistic story is like this. So we have one phase, we have the other phase, and the sum of those two phases is a constant, right, which does not depend on x. So that's an integral from a to b, p of y dy, plus pi over 2. So if this is equal to an integer times pi, then the corresponding sine functions are either equal or opposite to each other. And if you put CA equal to plus or minus, so CA prime equal to minus 1 to the n CA, then you will have a matching. And actually, it's easy to see that's the only situation when those sine functions can match for all values of x. So you need them to match for all x between A and B. All right, so so this gives us 1 over h integral from A to B p of y dy is equal to n minus 1/2 pi. And this is almost the condition that I had before in this theorem. The only thing is, if I choose p to be a positive square root, this is positive. So the right-hand side has to be positive. So this means that n should be at least 1. But I can also rename n by n minus 1. And this will be equal to n minus 1 plus 1/2 pi, where n minus 1 now starts from 0. So this will be the formulation that I had before. All right. So what's the conclusion? Now we have 5 regions, right? So in those 5 regions, what happens? We have in 3 of them those WKB functions. In 2 of them, we have Airy functions. So the asymptotics match if and only if this condition is satisfied. So up to now, it's all very optimistic. Now let's have a break, and maybe after the break I tell you that kind of the pessimistic side of the story, why I don't want to give a complete proof.
And now we see that the Planck constant is back to your condition, yes?
The
sorry, the Planck constant is back in my, yeah, the Planck constant is, the Planck constant is back in my condition, sure, yeah. It was, you know, like morning, the condition was not very good, yeah. The Planck constant is back in my condition as it should, absolutely. Yeah. Yeah, of course. All right, so let's have a break and let's continue after the break. All right, so let's continue. So let me finish with some remarks. So first of all, let me recall this formula that we derived in the beginning of the class. So if we substitute this WKB approximation, we obtain this formula. So for the WKB, we know that psi is in L2 of R. So we replaced it in the problematic regions by the Airy function. The Airy function is a nice holomorphic function. It's bounded on that region. So now for the asymptotics at plus and minus infinity, we fix the falling exponential, so it's in L2. Now what about this thing? For the WKB ansatz, I made, or I recopied from somewhere, a short computation which tells you that this ratio has the following, well, maybe not very appealing form, but so it's VW prime over 4 V minus E minus 5 over 16 V prime square over V minus E square times psi. So why is it good? Recall that we assumed that V prime over V and V double prime over V were bounded, right? There was that funny kind of assumption which was not that motivated. But now it is well motivated because this thing is bounded. So that's because V prime over V and V double prime over V are bounded for x large. And this means that for x, at least for x large, h minus e times psi, it is in L2, right? So here it is good. So that's the first remark. And it is proportional to h squared, right? Which is nice. So when we eventually estimate the norm, it will be proportional to h squared. However, now, to be honest, there is a problem in our story. So maybe let me draw again the axis with the turning points, A and B. Now, these are our 5 regions. So there is a forbidden region on the left and on the right. There is an allowed region in the middle, and there are 2 airy regions here. Maybe first of all, the question is, we should say, what's the size of those airy regions? It turns out that the size of airy regions, a good choice is something like a square root of h bar. So that turns out to be a good size of airy regions. But then there is still a problem, because the airy functions, the asymptotics do match with the WKB asymptotics. But the functions do not match here. And this is really bad, because here we have the second derivative the second derivative when the functions don't match, yeah, this will be horrible, right? This has roughly infinite L2 norm because of that. So for this reason, one has to introduce 4 more regions. You have to glue Airy, smoothly glue Airy to WKB if you want to do it really honestly. And actually that's why, frankly, I don't want to do it here. So in reality, you have to introduce 4 more regions. And in those regions, you should smoothly glue Airy and WKB and estimate the L2 norm of the resulting function h minus e times psi. It turns out that after you do that, one obtains an estimate. Actually, I lied to you in the formulation of this theorem. So if one does that, one does not get h squared. One only gets h bar to the power 9/8. However, I mean, qualitatively, this is good enough. It is faster than h bar. With some superior techniques, one can actually get h squared, but not with the technique that I described here. So the technique that I described here, this ugly gluing, it gives in the end some smaller degree. So so that's how the real life looks like when you start looking at it closely. Right. Nevertheless, let me one more time draw the beautiful picture. So that's the energy axis. So that's the window, E1 minus E2. So these are the WKB spectral points. That means solutions for the energy of this equation with h bar in. Sorry for missing it before. And now, near each of those points, there is a point of a true spectrum. And the distance is, if you use good techniques, is of the order of h bar square. If you use bad techniques, h bar to the power 9/8. But in any event, it will turn out that those distances are of the order of h bar, and those distances are much smaller when h bar is small. So that's the final qualitative picture of how it happens. So I think probably for today, if I'm not mistaken, in the exercises we'll look at the harmonic oscillator from that perspective. So we'll see an example in the exercises. All right. So I would like to finish this chapter. So we had some number of examples of explicitly solving the Schrödinger equation. And I would like to finish with one more example. There will be more examples in the problem sets. But one example which is very, very famous, and it was probably the first and remains one of the main examples of using quantum mechanics. So that's the 3-dimensional example of the hydrogen atom. So again, we'll find some mathematical angle for looking at it. So what is the hydrogen atom example? We have our Hilbert space L2 of R3, and the Hamiltonian is minus h squared over 2m. Now this is the mass of the electron. We assume that the proton is infinitely heavy, times the three-dimensional Laplacian, and minus 1 over r potential, where this q square is the square of the elementary charge. So I just keep those constants to have some physics intuition about it. But in principle, in this example, we can again put all those constants equal to 1 if we want. So before, it was really essential to have this h bar in the story, because we were looking at what happens when h bar changes. Now, this is no longer essential. All right. So let me recall that in polar coordinates, which are defined, for instance, by those formulas. So there is a distance and two polar angles. So this is the standard polar coordinate system. There is the following expression for the Laplacian. Let me write a Laplacian of some function psi. This is 1 over r squared d over dr, r squared d psi over dr, plus what? Plus 1 over r squared sine squared theta. I think d over d theta, and then probably again sine theta plus so there is this horrible expression. We're not going to use it full force. Maybe you will exercise a little bit more with it in the exercises. Of course, this coordinate system is not global. It has problems somewhere. At r equals 0, also it has problems, I think, at theta equals 0 and pi, right? So it is not a globally well-defined coordinate system, but at the moment it doesn't matter so much. So let me formulate a great theorem about this spectrum of the Schrödinger operator of the hydrogen atom Hamiltonian. So the spectrum is given by the following set. So there is a number of points on the negative part of the real axis. So here minus E naught, and then minus E naught over 4, and then so on, which accumulate to 0, and then union with 0 plus infinity. And maybe one should add that the dimensions of the eigenspaces corresponding to those isolated points of the spectrum are equal to n squared. And E naught is, if we keep all those units, is this expression. So that's the bottom of the spectrum. So let me recall that we did prove that Hamiltonian is self-adjoint or admits a self-adjoint extension. Also in one of the exercises, you looked at the Kato-Relic and you proved that H is bounded from below, so that's why the spectrum is bounded from below. Now the spectrum has this really intricate and complicated structure, which was discovered in the beginning of quantum mechanics. So this is a very complicated theorem. So we won't be able to prove it here today. However, we'll see a small piece of a proof. Namely, we'll be concentrating at this point. So this is an eigenspace which has dimension 1. So there is a priori one eigenfunction sitting there, or one line of eigenfunctions. So we'll look at those eigenfunctions which correspond to this point. But as you see, right, the spectrum is complicated, so one would need using different methods if one wanted to really prove that that's the spectrum. Well, so a small part of proof. Okay. So maybe let me do the following. So this will be like, it will have several steps, even that small part will have several steps. And let me look at step 1. So for some, at the moment, unknown R0, so let me consider the exponentially falling functions, which only has a dependence on the radius, exponential minus r over R0, and I consider them outside r equals 0. So then let's compute the Laplacian of such a function. Well, so for that I prepared for you the expression in polar coordinates. Now there is no dependence on all those angles, theta and phi, so we should just apply that part, right? So we have 1 over r square, d over dr, and here r square, d over dr, exponential minus r over r0. Well, what does it give? 1 over r squared, d over dr, and here r squared minus 1 over r0, exponential minus r over r0. And what does it give? It gives, in the end, 1 over r0 squared, exponential minus r over r0, right? Minus 2 r, 1 over r0 r, exponential minus r over r0. Is it right? Okay, so maybe one thing. So we'll now be doing something with this expression, but could you note and then later on recall me how this expression looks like, because I'll need it later on and I'll probably erase it in the meantime. Okay, so now, so what about the Schrödinger equation, right? I want to solve, so I want to know, I claim that outside r equals 0, so this psi, for some good choice of r0, solves the Schrödinger equation for some energy. So if I multiply by minus h squared over 2m, what I obtain is the following. So will be h squared over m r0 1 over r, and this is just the value of psi, right? And then with the minus sign, minus h squared over 2m r naught squared times psi. So now if we want to solve the eigenfunction equation for this operator, right? So we want this guy to be equal to q squared over r. And this would imply r naught equal to h squared over m q squared, right? And so this expression will be then the value, the negative value of the energy, E naught. And if we substitute this R naught, then we'll get what we want, right? Q to the fourth over 2m. mq to the fourth over 2h squared. Yeah, sorry, with those quantities. Right. All right. So this this function does solve the Schrödinger equation for this operator for the value which I declared. Now, are we done? Are we not done? In fact, we are not quite done. It's more like the beginning of the story. So now what remains to do? Show that psi is actually in the domain of H. So this is not quite obvious because you see, maybe I especially stressed the fact that R is not equal to 0, right? So we don't quite know what happens at R equals 0. Maybe something very bad happens. So let's try to analyze it. So here we'll make a break in the proof, and I will show you the following proposition. Let's assume so psi is NL L2 of R3. Psi is smooth outside the origin. The Laplacian of psi is then well defined outside the origin and belongs to L2. And the limit R squared psi of R and whatever the other variables, whatever they are, limit R squared psi d psi over dr R to 0 is equal to 0. So then psi belongs to the domain of the Laplacian, and so let me write this somewhat kind of ambiguous formula. Well, so what we mean by that, right? We already have maybe it's better to write it in this way. Let me call phi the Laplacian of psi as an element of L2. And now, since we say that psi belongs to the domain of the Laplacian as a self-adjoint operator, so then that's the L2 element which results by acting on psi by the Laplacian. And it coincides with that function that we defined by smoothly differentiating outside 0. So that will be the conclusion. So actually, then the naive action of the Laplacian, as we computed it here, it does give you the correct result. Okay. So proof. So let me choose some test function in C infinity of R3 with compact support. And let me consider the following integral. So I take a Laplacian of chi and I multiply it by psi and I integrate it over R3. So this is all well defined, right? So this guy is a compactly supported function on R3, so it's in L2, so psi is in L2, so this is a well-defined quantity, right? So now I would like to subtract from it an integral over R3 of this element phi multiplied by psi. Right. Okay. So phi is this naive Laplacian. Maybe what I will do, I would like to show that this is actually equal to 0. So I will write it as a limit. Epsilon goes to 0. Sorry?
Where is epsilon?
No, but there is no epsilon. Yes, at the moment. Of the integral over R3 minus the ball of radius epsilon of Laplace chi psi minus phi psi d3x. Now those guys, they are all smooth. So for this, there is a so-called Green's formula, right? So you have a domain with a boundary. You have Laplacian one function times the other minus Laplacian of psi. Sorry, here should be chi, right? Yeah, sorry. So minus Laplacian minus chi minus the first function times Laplacian of the second. At the infinity, one of those functions chi vanishes, so I can think of it as an integral in the big ball of radius capital R, and here there is a small ball of radius epsilon, right? So the integration domain is actually equivalent to a big ball inside there is a small ball, and that's my integration domain. So this is equal by Green's formula. And here I must admit I never know what's the correct sign. Maybe someone here knows the correct sign. So that's over the sphere of radius epsilon. And here I will have d chi over dr psi minus chi d psi over dr. And here the area integral over the surface of the sphere, right? So that's how the Green's formula looks like. So anyone knows what's the correct sign? It's anyway under the absolute value, so it doesn't matter, but just to be, well, whatever. That probably also depends on how the orientations. The physicists should know those formulas. So, okay, so there is one correct sign, which is anyways irrelevant. Okay, now, so chi is in C infinity, so chi and the derivative of chi, they are all bounded by some constant. Now, so this is all bounded, so this is a limit, epsilon goes to infinity. And so there is a constant, which is a common bound for the derivative and for chi, times the area of the sphere, and times the max of, maybe here I should say epsilon square, psi of epsilon d psi over dr of epsilon. So this limit is equal to 0 by those assumptions, right? So that's why we wanted r squared times psi of r and r squared times d psi over dr. That's for those things to vanish. So this is equal to 0. Now maybe just a remark in the middle of the proof. Suppose you take a function of this form. Then it's easy to see that psi is an L2 of R3, right? You take its square, you get a denominator R square, but in the integration, you have an R square factor, so it's fine. Now, moreover, you can check that if you take the naive Laplacian outside R equals 0, so it also has like kind of mild singularities, and so this is also in L2 of R3. So there is no problem with that. However, this condition is not satisfied because you see, you differentiate this 1 over r, you get 1 over r squared. So the limit r d psi over r squared, when r goes to 0, is non-zero. So you see, and then the argument that I'm now trying to explain is going to fall. In particular, this guy is not in the domain of the Laplacian, even though naively it is. You compute the Laplacian, you get some reasonable expression. This expression is square integrable. Now what? But then, well, there might be still problems. All right, so okay, so those two expressions, they are the same. So now let's run the following argument. So I have Laplacian of chi times psi d3x integral over R3. Now this is an L2 function, this is an L2 function. We can do the Fourier transform and use the Bessel's identity. So this is equal to the integral over R3 Laplacian chi tilde times psi tilde d3k. Now Laplacian on the Fourier transform, we know what it is, right? So it is minus k squared, right? So times chi tilde times psi tilde d3k. Well, on the other hand, we know that this is equal to the R3 integral of chi times phi d3x. Again, these are two L2 functions. We can run the Fourier transform. So this is equal to R3 chi tilde phi tilde d3k. But now this equality is verified for all chi in compactly supported C infinity. But this is actually L2 dense in L2. So this implies, after some thinking, that actually, so this implies that there is this L2 equality that phi tilde is minus k squared times psi tilde. But this is more or less the true definition of the Laplacian, right? We define the Laplacian by Fourier transform and then multiplying by minus k squared and then the inverse Fourier transform. So this implies what we want. So psi is in the domain of the Laplacian, and this element phi is the image of psi under the action of the Laplacian. Well, now let's continue. Now let's continue the proof of this theorem. We have our function psi is equal to exponential minus r over r naught. So so it clearly belongs to L2, right? It's square integrable. Now, could you recall what was this thing? Right? It was something. It was proportional to exponential minus r over r naught, and then there was a coefficient. What was the coefficient? One over r0 square minus
2 over
r0r. Okay, thanks. All right, so that's the naive Laplacian. It is well square integrable. Again, right, we take a square of it, we get the denominator 1 over r square, and then in the integration measure over r3 we have r square. So there is no singularity in the integral, so it is in L2 of R3. Now limit R square psi of R when R goes to 0 is equal to 0, that's obvious, and maybe more critically, d psi over dr limit is also equal to 0, because that's in both cases, that's just the exponential. So all the conditions are verified, and this means that psi in the domain of the Laplacian, and then the naive Laplacian, the Laplacian that we computed, is actually the image of psi under the Laplace, under the self-adjoint Laplace operator. Now, the last step in the proof. Actually, that last step, there are two different ways to do it. One way is naive, and the other one is high-tech. So the naive way is as follows. So we want to know whether whether it is in the domain of the potential. So of course, this is easier to check. V psi is minus q square over r, exponential minus r over r naught, and simply to check whether it's in the domain, we should check whether it's square integrable or not, right? So here, it's not a differential operator, it's a multiplication operator. So here, it is in the domain, it is in, it's square integrable, hence, psi is in the domain. Now, what would be the high-tech way to do it? Let me recall that by Kato-Rehlich, right? We actually don't need to check it. At some point, we checked the complicated Kato-Rehlich estimate for the Laplacian and exactly that potential. And Kato-Rehlich implies that the domain of V, what am I saying? No, Kato-Rehlich implies that the domain of H is equal to the domain of delta, right? So that's what Kato-Rehlich says. Is it right? So once the estimate is verified, so we start with an operators A and B, right? And A plus B is a self-adjoint operator on the domain of A. So that's what Kato-Rehlich says. So this follows from the estimate. So therefore, and also the Kato-Rehlich estimate also says that the domain of delta is contained in the domain of V. So something which is in the domain of delta is automatically in the domain of V, right? So that's the Kato-Rehlich. So therefore, the last step would be to say minus q square over r acting on psi. This is just a naive calculation that we have done before. And this is equal to minus E naught psi. And now this is inequality for the action of this complicated self-adjoint operator on our function in its domain of definition. So it's a true eigenvalue, it's a true eigenfunction. Well, so we'll stop here today. Of course, right, we proved only some portions of theorems, so these are big theorems we were discussing today. We kind of saw a little bit of how it works. And what will happen next time, we'll start discussing the time-dependent Schrödinger operator, or time-dependent Schrödinger equation. And also we'll start discussing the path integrals. So that's the big thing in quantum mechanics. And this is probably going to be the last chapter. We'll see whether towards the very end we'll have a little bit of quantum mechanics and geometry. But let's see how it goes. All right, thanks. That's it for today.